Okay, got it. Okay, there it is. Okay, hello all. So I'm Raul Gomez, and I work as a data scientist at Shutterstock. Many of you might know Shutterstock, but in case you don't, it's a huge content marketplace with different types of data. But in this work, I'm going to focus on images. So Shutterstock images with rich annotations are super relevant for the computer vision community where I come from, but they are also relevant for this RecSys community, so super happy to be here presenting our latest developments with you. Okay, so this is the outline I'm going to follow. I'm going to start introducing the problem and explaining what image marketplaces and content creatives our users are. Then I'll get into explain our solution and why it's different from other RecSys and challenging. Then I'll continue with the data, the model, to finalize with experimentation and results. Okay, image marketplaces and content creatives. What are image marketplaces? Well, there are huge online catalogs. In Shutterstock, we have more than 400 million images, and they are global. We have contributors and also users from almost anywhere in the world. And of course, content is very diverse in terms of semantics and visual styles. And how content discovery works at Shutterstock? Well, it's mainly based on search engines, which run content based mainly on popularity. And we have to say that content discovery at Shutterstock is very important now, socially speaking. And why is that? Well, because it's the first stage in many content creation pipelines. So, of course, any biases or, like, for instance, visual style preferences in content discovery and an image marketplace can be passed on to many creative processes. Okay, so now let's talk about our users. Our users, of course, are diverse in terms of visual preferences, but importantly, they are creatives, which means that their interests are linked to the projects they work on and change rapidly and abruptly, which, of course, is a challenge for recommendation systems. And to find content relevant to those projects, those creatives navigate the catalog using a search engine, right? So, for instance, here a user gets in Shutterstock and he's searching for people images. And he's getting images ranked mainly by popularity. So you can see that results are very diverse. He's getting from illustrations to more like stocky images, to more casual images or studio portraits with colorful backgrounds. And then, of course, he can use like search filters to refine those search results. Okay, let's get into the solution. So basically, our hypothesis is that those creatives have long-term visual style preferences which are transversal to the semantics of the projects they work on. And we aim to learn those preferences based on their historical activity in the marketplace. And then personalize search results to match each user-preferred visual styles. So what's the advantage of this approach? Well, the main advantage is that users can benefit from recommendations while they rapidly shift between projects using the search engine. And then at the same time, they can use any search filter or any search functionality. And second, that recommendations are user-specific, which boosts the diversity of the content served at Shutterstock overall. And what are the challenges? Well, the main challenge is defining those image features that are stable across creatives for different projects. Okay, let's get into the data. So basically, we learn from user clicks on images during the 6-month time window. Specifically for this experiment, we use 10 million clicks, which we split in a train set and a test set containing the latest 1 million clicks. As user features, we use an individual user ID, an organization ID, the user country, language, and subscription to the platform. And now the interesting part, image features. So we use image categories, which are semantic verticals, such as nature, symbols, or illustrations. We use the contributor country. We use the image dominant colors. We use image angle features, which are categorical features encoding the photo angle based on handcrafted image keywords. We use photo style features, which are also photo styles based on handcrafted keywords. And we use deep features, which in this case are visual features extracted by an in-house trained CNN with the top marketplace search queries and results. Okay, so let's get a little bit deeper in those image features. What is the main requirement of those image features so that we can learn the so-called long-term visual style preferences? Well, the main requirement is that they cannot encode project semantics. Why is that? Well, because those are too discriminative compared to style features, and that would prohibit learning user-preferred styles. Like for instance, imagine that we use image keywords to encode images. At the end, the model will end up learning which keywords are relevant for the projects a user worked on during the training window, and therefore the recommendations wouldn't be relevant for further projects. But then also we have to say that those features, they don't need to be stable across projects for all users, since the model can learn which features or feature interactions are relevant for each user. Okay, now let's talk a bit about those features encoded in semantics. So we do have categories which encode styles such as illustrations, but also some semantic verticals such as nature. But we have observed that they are stable across projects for many users, and also including those within the image features allow learning multiple semantic verticals and visual style pairs that resonate for a given user. And we also have deep features, which of course, they tend to contain very rich and discriminative visual information, but the features used here do not encode fine-grained semantics, so they are compatible with learning long-term style preferences. And actually, we propose a metric to monitor that, which I will explain next. Okay, the model. So the model has a two-tower architecture that learns users and image representations in the same space. So first, we learn a representation for each one of the features, then we concatenate those, and we process them with a set of fully connected layers until they join embedding space. In the image encoder, we also use cross layers, which are used in parallel to the MLP and that facilitate learning feature interactions. And all the model is training with a contrastive loss, minimizing the distance between like user and image positive pairs, which are image clicks, and maximizing it between negative ones, which are random elements in the batch. Okay, the experimentation. So we evaluate the model with a set of metrics. First one is accuracy, which, well, probably I don't need to explain that, but like measures if a recommendation is within the tested clicks for a given user. Then we have two metrics evaluating overall diversity of the recommendations, catalog coverage, which measures the percentage of the tested image in the top recommendations, and effective catalog size, which measures a similar thing, but at different K, in K the position in the ranking. And then we have visual diversity. Visual diversity is the average distance within the deep features for the top 10 recommendations for each user. And it's inspiring in a measure in a metric to measure the diversity of GAN-generated images. And basically, it measures how diverse recommendations are for each user in terms of deep features. And why is that important? Well, because we aim to learn recommendations based on a style, so we want them to be visually diverse, which means not fully driven, but deep features in this case, so that recommendations are relevant for projects with different semantics. Okay, so here we see a set of models training with different subsets of image features. And let's analyze them one by one. First, we see visual style RecSys deep. This is a model trained only with deep features as image features. And we can see that it gets the lowest visual diversity. And that's expected, and we can consider it the lower bound, because actually any model leveraging successfully any other type of feature should score higher on this. Then we see visual style RecSys, all by deep. This is a model that has been trained using only image shallow features. And we can see that it gets the highest visual diversity, and it gets lower accuracy and diversity than visual style RecSys deep, but still significant. So we can draw three conclusions out of this. First, that shallow features are relevant for recommendations. Second, that deep features are key. And finally, that visual diversity allows monitoring deep features' influence in the recommendations. Finally, we see visual style RecSys all features, which is our final model. And we can see that it gets significantly higher visual diversity than visual style RecSys deep, and it gets the highest accuracy and diversity metrics. So it successfully leverages features of diverse natures to provide relevant and diverse recommendations, and as a result, diversity among content served results in a higher percentage of Shutterstock catalog being exposed. So here we see some qualitative results. We see top 4 recommendations for 4 different users and the sustainability and technology queries. And we can see, for instance, that user A has a preference for stocky images featuring people and the gastronomy semantic at vertical and close-ups, while user B has preferences for wide-angle pictures, greenish colors, and digital art. Meanwhile, user C has preferences for structured close-ups and like bluish colors, and user D has preferences towards like signs, symbols, illustrations, and isolated objects with homogeneous backgrounds. Note that the model does not limit to learn a single preferred style per user, but multi-preferred styles. And as a result, recommendations are not only diverse within users, among users, but also within them. So, for instance, note that user A has a lighter preference toward illustrations, while user B a light preference toward isolated objects. Okay, so that's all. Thanks for listening. Feel free to reach out to me to chat, either here or online. And if you're interested in more details, a technical report with further details has been published.
Thank you very much. Now we have questions. The most popular question, how do you select negative examples?
How do you select, sorry?
How did you select the negative examples?
Negative examples are just like random elements within the batch. So basically, we learn solely from user clicks on images. Then we build a training batch, just with a random subset of user and image clicks. And we use all the rest of elements in the batch, all the rest of either user or image elements is in the batch as negative. So they're random.
Okay, thank you. Question 2, second most popular. What are the advantages of using image type interaction and user features over purely content metadata-based recommendation? I think basically summarize your talk. I would say that the nature of the question. But it's most popular. What is the benefits of using
clicks?
User image interaction data versus purely content metadata, like tags, objects?
Yeah, well, actually, we are using content metadata to encode images. We don't use any individual image ID. So we use like image colors, categories, some selected keywords, deep features, and so on. As user, we do use an individual user ID because we want that the recommendations are totally personalized to boost diversity. But I don't see the correlation with that to use image clicks or other types of user interactions.
Thank you. Maybe one more question. That's a really interesting question from Marta Larsen. You're trying to capture a signal orthogonal to the semantics. Is the model picking up some sense of image quality? What do you think? It's just like visual nature or quality, in fact?
No, I don't think the model is especially focused on image quality. Although, of course, the combination of different image features that the model is learning could have a correlation with image quality, and it probably has. So the correlation is there, but not explicitly, let's say. So actually, for image quality, we are relying in other text. So basically, at the end, we are going to use this model, this RecSys, to re-rank a search of results coming from, let's say, candidate generation model that can be a deep model per se, or can be just a plain search engine. So we are relying on that for image quality.
Thank you. Lots of good questions. Hopefully, you can answer them later online. And now we're switching to paper number 5.
Thanks.
Yeah. Thank you very much. So one more.